Hi, I'm Ed Marzell, President and CEO of Kenexis. Today's presentation is an encore performance of a presentation that I gave at the ADIPEC 2013 conference in Abu Dhabi. This past November is when the presentation was given. The topic of the presentation is a case study implementing performance-based fire and gas detector placement per ISA Technical Report 84.00.07 on a sulfur recovery unit. When designing systems in accordance with the ISA Technical Report for Fire and Gas Systems, you are performing what is called a performance-based design basis. So you're using targets. You're selecting performance targets and then verifying that these targets have been achieved. And we're going to be doing this for a sulfur recovery unit. And sulfur recovery units are quite hazardous. They're used frequently within the oil and gas production industry and the oil refining industry to remove sulfur from hydrocarbons. Well, that's what needs to be done in industry, and then the sulfur recovery unit takes a stream called acid gas, or a waste stream that contains a lot of hydrogen sulfide, which is a very toxic chemical, and converts that hydrogen sulfide back into elemental sulfur. So in order to determine the overall risks posed by this facility and how the fire and gas system helps to mitigate those risks and the performance of that gas detection system specifically, we're going to need to perform an analysis of the hazards, and that's going to include some dispersion modeling. And then we're going to look at the detector coverage, how the detectors are laid out initially, and then what our final recommendations are. And then compare the results of the traditional method, which is what was used for the original design, kind of using rules of thumb and expert judgment, and compare that against the placement that was calculated using performance-based methods. We executed this project in accordance with the ISA 84.00.07 safety life cycle. That life cycle contains 11 steps for designing, and if all these steps are executed properly, that should result in a functionally safe fire and gas detection system. The first step is identifying the areas of concern, and basically that was limited to the sulfur recovery unit. That was our scope of analysis. All of the equipment items in that unit were considered to determine whether or not fire gas detection was going to be required for that equipment. For steps 2 through 6, we performed dispersion modeling. We analyzed each piece of equipment. What type of equipment is it? Where is it located? And then based on that assessment, we assigned performance targets that were a function of the severity of any releases that might result from that equipment and the frequency at which those releases can occur. Steps 7 through 11, we took a look at the existing detector layout that was performed using expert judgment and other design heuristics. And then we used the Kenexis Effigy fire and gas mapping software to assess what level of coverage was provided. And we did this for an existing case and also for a recommended case. Now, within the scope of this study, the client that we performed the study for was not really interested in assessing the probability of failure on demand or the safety availability of the fire and gas system. So that's not going to be part of the case study that we're discussing today. Hydrogen sulfide is the key chemical in this process that we are concerned with, and we want to make sure that the employees at this facility are not exposed to this chemical. As I mentioned previously, the sulfur recovery unit is going to convert the gaseous hydrogen sulfide to elemental sulfur. We're basically going to burn it. We're going to oxidize it, the H2S with oxygen, and that's going to convert the inlet materials, the input materials, from H2S to elemental sulfur plus H2O water. Now, There are varying concentrations of hydrogen sulfide in the different pieces of process unit in this equipment. The acid gas or the sour water gas can be up to 75% H2S, whereas the tail gas is usually going to be less than 1% H2S. So there's a broad range of concentrations of this material in the different process vessels. Now, with respect to hydrogen sulfide itself, it is an extremely toxic chemical. It's a broad spectrum toxin. It's a pulmonotoxin, meaning it affects or destroys your lung tissue in concentrations as low as 300 parts per million. And it is also a neurotoxin in concentrations as low as 500 parts per million. So low concentrations of this chemical can have very, very adverse effects to employees and any people in the surrounding areas. So making sure that this chemical is controlled and that releases don't occur, and if they do occur, that they're quickly detected and mitigated, is going to be very important. We started the analysis by creating design basis scenarios. And a design basis scenario, we're looking for design basis hazards where a release is at an incipient stage in the gas cloud development. So at that incipient stage, we want the gas cloud to be detected to allow personnel egress. The predominant H2S containing streams that we looked at were acid gas streams, sour water stripper gas streams, and the tail gas streams. So those were the three different types of releases that we modeled. When we did our modeling, we used several different equivalent hole size diameters to represent the range of leak sizes that could occur. For acid gas or sour water, we were concerned with a 5 millimeter hole size being our incipient leak. And for tail gas, we modeled 25 millimeters because of the lower concentration of H2S in the tail gas stream as opposed to the acid gas and the sour water streams. Okay. Small leaks have a capability to create the hazardous situation in areas where the concentration of H2S is lower, whereas larger leaks are going to be required to create a hazardous scenario for less concentrated streams. But in either case, even for the most concentrated stream, a small leak is going to create a smaller cloud, and thus it's going to be harder to detect. So you need more detectors to detect a smaller leak than you do to detect the larger leak. Thus, if you're appropriately covered for small leaks, you will inherently also be appropriately covered for larger leaks. After we designed the design basis release scenarios, we estimated the consequence beginning with performing dispersion modeling. So for each one of the design basis scenarios, we looked at the concentration of H2S in the material that's being released, the temperature and pressure at which the material is being released, hole sizes, and the ambient weather conditions at the facility. We did this modeling using similarity dispersion models. So something like, well, specifically for this project, we used FAST from DNV, and that's an example of a similarity dispersion model as opposed to something that would be more complex like computational fluid dynamics, which would be required indoors, but we felt that the similarity dispersion models were appropriate for the relatively widely spaced outdoor facility that we were analyzing. Now, we ran our dispersion models out to 3 different endpoints, and at least one of the endpoints is different from what would be done in a traditional quantitative risk analysis or a QRA study. We modeled life-threatening effects at 700 ppm, and we modeled injury at 100 ppm, with 100 ppm being the IDLH, immediately dangerous to life and health level from NIOSH, or the National Institute of Occupational Safety Hygienists in the United States. And that's set more of as an injury set point. Also, we modeled the gas cloud sizes to 10 parts per million, And the reason we modeled that is the gas cloud size that is detectable. So the 10 parts per million is going to be our alarm set point in our gas detection system. So that gas cloud size is going to represent the size of a cloud at the limit of detection or alarm capability for most detection methods that are capable of detecting H2S clouds. After all the dispersion modeling was done, we created a table to show the results of the dispersion modeling. And as you can see in the table, there are 4 of the scenarios that were modeled for the study. And for each one of those models that was run, there's a description of which scenario specifically it was, the release rate, the duration of the release, and then a demonstration of the distances to the end point for the injury, which is 100 ppm, and also for detectability, which was at 10 ppm. And you can see that the gas cloud size that is detectable is significantly larger than the gas cloud size that can cause injury. So for the first scenario, which is a 5 millimeter leak of acid gas, you'll see that the distance from the leak point where an injury can occur was 100 feet, whereas for that same release, the distance at which a gas detector would go into alarm because of the release is 540 feet. So the gas cloud length that is detectable is more than 5 times greater than what can cause injury, and what is expected to cause fatality is even much smaller still. This is the reason that we need to model the detectability gas cloud in addition to the injury size gas cloud, because you're much more detectable than what will cause injury. As part of the output of the project, we generated different views of the acid gas release scenario to help illustrate the size and dimensions of the gas cloud. The first view that you'll look at would be a dispersion cloud side view. So we're going to look at the side of the cloud to determine how highly elevated it will be at the different distances downwind of the release. The second view that we considered in our analysis and in our reporting is a more common view, which is the footprint. So this would be a representation of the gas cloud looking down from above. And that would represent the area on a plot plan that the gas cloud would cover. Okay, the dispersion modeling that we performed and the subsequent risk integration that we're going to do inside our effigy fire and gas mapping software is going to account for wind speeds and atmospheric stabilities. So we were required to obtain a wind rose to look at the different wind speeds and wind frequencies of the different directions at this particular site. Now, toxic gas clouds are going to be very sensitive to wind speed, and they're also sensitive to the atmospheric stability. And the gas clouds that we showed you on the previous few figures were based on a F stability, which is representative of nighttime stability, very stable atmosphere that you would expect at night, and a low wind speed of 1.5 meters per second. These atmospheric conditions combined are what we would consider to be unfavorable and would result in a larger gas cloud. The next part of the design basis consequence assessment is considering the frequency at which releases will occur. Frequency assessment for fire and gas mapping, performance-based fire and gas analysis, is not a predictive process, it's a statistical process based on past releases. So we're not going to do a LOPA to try to calculate or estimate how frequently we expect the leak to occur. Instead, we're just going to use databases of equipment leak rates to determine what has happened historically. And although the leak rates are equipment based, we're going to sum all of the different equipment items up that would generate a certain type of design basis scenario. So as you can see, we've created a table where we look at the different types of equipment and the scenarios associated with those equipments and assigned an appropriate release frequency representing that equipment type. Based on the risk analysis that was performed, we assigned performance targets, or what are referred to as gas grades, to each of the different areas or zones that contain the releasing equipment. The gas grades define the ability of a function to detect alarm and mitigate the consequence if necessary. We used a semi-quantitative scoring procedure and applied that procedure to each leak source. For more details on the procedure, you might want to download a copy or purchase a copy from Amazon. The Kenexis Fire and Gas, or FGS Design Handbook, which has an appendix that includes a detailed description of the procedure that we use to assign performance targets. In this case, the grades A through C are going to have coverage targets of 90%, 80%, and 60% accordingly. So A would be a high level of risk, something like rotating equipment at high pressure, whereas a C would be something where the toxin concentration is relatively low. The equipment, something like piping or valves, has a lower frequency of release, and the pressures and temperatures are going to be lower, again driving down the frequency and the size of the gas cloud if a leak were to occur. So all of those, the grades A, B, and C, based on the risk analysis process, were assigned to each of the different process sections. Again, the performance grade determination process was performed for each section, and tables were generated using our FGS Design Basis toolkit that would assign a grade to each of the process sections, and that table can be shown, or is seen here. After selecting grades, we mapped all of the gas releases using our FGS assessment tool, and that tool being the Kenexis effigy software, which is in the KISS, or Kenexis Instrumented Safeguard suite of software applications. The inputs into the tool include things like equipment layouts, release frequencies, dispersion modeling results, gas risk footprints that are going to be generated by aggregating the release, and then wind distributions. So we enter all of the data in, and the software aggregates the results in different ways. So we're going to look at two different types of coverage, including both the geographic coverage and the scenario coverage, both of which are defined in the ISA 84.007 technical report. The first figure that we're going to look at is the unmitigated gas release, and again in the scenario coverage format. So what you're looking at is, again, the unmitigated risk profile, or the unmitigated geographic risk. So you'll see a plot that has different colors, and those different colors represent the frequency at which a gas cloud will exist in a certain location. And this figure for unmitigated risk it does not include the beneficial effect of the gas detection system. So dark red would represent leak frequencies of approximately 1 to 10, or 1 in 10 chance per year. And then each color change represents a half order of magnitude decrease in frequency. So as you can see, right in the middle of the process area, there's a big area of dark red indicating that the risk in this area is significantly high. In the next figure, what we show is the mitigated risk profile. So let me step back a little bit and explain how these figures are drawn. Each gas release is going to have roughly the shape of an oval with a certain downwind distance and a certain crosswind distance. That would be one release scenario from one point, one set of weather conditions. Well, as we mentioned early, we're going to be releasing material from from multiple different pieces of equipment. We're going to be releasing equipment at different weather conditions, and we're going to be releasing material in different orientations, whether the material is released due north or to the west or to the east is going to change, and we need to consider all of the possible orientations of a release. And we also need to consider, as I mentioned a few slides ago, the wind directions. So the way the F&G software works is it's going to more heavily weight releases that occur in the direction of the prevailing wind as opposed to against the prevailing wind. So all of that windrows information is also going to be considered when putting this graph together. So each one of those ovals is an individual scenario. And what you see on this figure is an amalgamation of those probably hundreds of thousands or possibly millions of scenarios are all essentially laid on top of each other. And the frequency associated with each one of those releases for each point on the map gets summed up to generate the graph that we saw previously and also this graph. But the difference with the mitigated risk graph that we're looking at now is that the scenarios that intersect with a gas detector, so those scenarios where the gas cloud is going to be detected, have been removed from the scenario. And what you have left is a figure that represents the frequency at which gas clouds will exist that are not detected by the gas detection system. And what you're looking at here is the existing or the starting point for this facility. In addition to drawing the map, there's also a calculation of what is the frequency of releases that has been detected. So with the existing 8 detectors in this facility, we were able to detect 58% of the releases. Well, unfortunately, this area was zoned as a grade A. So we need to be able to detect at least 90% of the release scenarios in this area. So the existing design, as placed by expert judgment and rules of thumb, failed to achieve the desired performance target. As a result, we had to add more detectors and move detectors around. Well, for this specific project, part of the scope of the study was to not move the existing detectors. So we could have improved performance by moving detectors around, but instead all of the existing detectors stayed where they were and we had to add more detectors in other locations. So for an analyst looking at this type of drawing, you'll want to put more detectors in an area where the risk is higher. And it's very easy to see where the risk is higher by the color coding on the map. So areas here that are shown in red are going to be the highest frequency of release, and that's probably where we want to put more detectors, as opposed to areas that are already blue or purple, where the risk is probably already acceptably low, so we don't need to focus in those areas. This final figure represents the recommended detector layout. And again, we're looking at scenario coverage instead of geographic coverage. And we're looking at a mitigated geographic risk profile. So what you're looking at, again, is the frequency at which gas clouds will exist that are not detected by the existing gas detector array. So in order to achieve the customer's performance target of this zone of 90% scenario coverage, we had to move up to a total of 15 detectors, placing 7 new detectors that were not in the existing design. By adding these new detectors, we were able to increase our scenario coverage to 90%, which allowed the tolerability of risk goals of this facility to be achieved. In a tabular format, you can see that the results of the study showed that the existing 8 detectors were only capable of achieving a 58.1% coverage, and that did not achieve the performance target. So the recommended design resulted in 15 detectors, and that exceeded the 90% coverage target, bringing the coverage up to 90.1%. Some things to note about the results. This case study did not include the consideration of any automatic actions being taken as a result of activation of the gas detection system. We're looking at alarm-only coverage. Again, we did not move the existing detectors around. We simply added new ones to achieve the performance targets. If we would have moved detectors around, we probably could have achieved that 90% target with fewer than 15 detectors. But that's a decision that the customer made at the beginning of the project, and that was part of our design basis. Okay. And that concludes our presentation. Thank you for viewing the presentation, and before leaving you, let me give you a couple of references for a little bit more information. First off, I would highly recommend viewing the ISA 84.00.07 technical report, which is application of ISA 84 or IEC 61511 for safety instrumented functions in fire and gas systems. And I would also recommend reading the Kenexis case study on H2S hazard analysis and assessment, as was performed for a U.S. refinery sulfur recovery unit. And that paper is going to be available at our website for download. And finally, also, I would also recommend that you download the Kenexis FGS Design Handbook, which is also available on our website. For a printed copy, you can go to Amazon.com, and there will be an ISA version available hopefully later this year.